So for this class, in using our kinematic equations, we're going to focus on two basic types of motion, either constant accelerated motion or constant velocity motion. So let's start by thinking about the first of those. So let's assume you've got constant acceleration, meaning that the acceleration value is constant. And so what we'll do is we'll set this up thinking one-dimensionally about what's going on in the x-axis. So we'll label everything with x components here. I know that the x component of the acceleration is nothing more than taking the x component of the velocity, taking its derivative with respect to time, but I can undo that equation, basically multiply the dt back over so that I'm left with this, and now I can integrate. So if I integrate both sides of this equation, again, because my acceleration here is constant, I can pull it out of the integral. I'm left with the integral of dv, the integral of dt. Both of those are just going to leave me with the x component of the velocity and the time. So I've got the x component of the velocity equals the x component of the acceleration times time plus c, where I need to figure out what this constant of integration is. At t equals 0, whenever I started my clock, my object was moving with some initial velocity in the x direction. When I plug that in, velocity at t equals 0 was just v naught x. That term disappears. It tells me that c is equal to v naught x, and so when I come back and plug that in, I get this equation. So here's one equation. It only applies when I have constant acceleration, and what it does is it gives me the x component of the velocity as a function of time. Well, once I've come this far, again, because I know how the x component of the velocity relates to the x component of the position, I can play the same game. So again, the x component of the velocity is dx dt. Again, I'm going to multiply the dt back over. It's going to leave me with this expression when I plug in for vx, so plugging in that previous equation that we solved for. And again, now I can integrate on both sides. I've got a couple of terms on the right, a single term on the left. So when I integrate dx, I just get x. Again, v naught x is just some value. It's what the value was of the x component of the velocity at t equals 0, so it's just a number. I can pull it out. I'm left with the integral of dt, that's just t. And then here, again, I've assumed that the x component of my acceleration was constant. That can get pulled out of the integral, and I'm left with the integral of t dt. And I know that that is 1/2 t squared. So here I've got my equation after I do the integration. Now I just need to figure out what my constant of integration is. Again, we'll say at t equals 0, the position of your object was someplace that we'll call x naught. So again, the naught here just means initial, the initial position, in the same way that the naught here is a 0, just meant the x component of the initial velocity. So plugging that in, again, x naught's where it was when t equaled 0. Those two terms disappear. I get that the integration constant is just x naught. And so I'm left with a equation that will tell me the position as a function of time. So I've got an equation for the velocity as a function of time and for the position as a function of time. I can take those two equations and eliminate time. So the easiest thing to do is take my velocity equation and solve that for t, then go plug it into my position equation. Again, there's a lot of algebra. I need to make sure I do things correctly when I'm squaring this term. But what you end up with terms that cancel out when you add things together. And it simplifies down to something reasonably easy to deal with. And so I get x equals x naught plus vx squared minus v naught x squared over 2ax. And what we'll tend to do is simply rewrite that into this form. And so this is basically relating our other variables just without t, because we've eliminated time here. So what this means is, effectively, when we have constant acceleration, there are three equations. But of course, velocity, position, acceleration, these are all vectors. And so there's really three equations that I'm tying up in this notation. So there's an x component equation for each of these. There's a y component equation for each of these. There's a z component equation for each of these. So we, again, won't deal much with the z component, but of course it's there because we live in a three-dimensional world. And so again, just recognizing that when we have the vectors, we can break that up into whichever set of component equations we need, and in some problems we may need more than one set. So that was one type of motion, constant acceleration. The other type we'll deal with is constant velocity, and this is really constant acceleration just with a very special value. So here the x component of the acceleration is not only constant, it happens to be constant with a value of 0. And so if we take our equation for the x component of the velocity as a function of time, if the acceleration is 0, that just tells us that the x component of the velocity at any point in time is the same as what it was at the initial. This is another way of saying that the velocity doesn't change, which is what we assumed. We assumed we had constant velocity motion. So this is basically just checking that what we've done makes sense. If I take my acceleration value of 0 and plug it into my position function, then again this acceleration term disappears. I know that I only really have a single velocity because I'm traveling at a constant velocity, and so instead of writing that as a v0, which implies that it would change, I'm just going to write it as a vx, which is another way of saying that it's always constant here. And so what this means is I have effectively one equation for constant velocity motion. And again, we've set this up with the x component, but there's nothing sacred about that x component. And so there's really three equations here, one for the x direction, one for y, one for z. When you think about your kinematic problems, if you have constant velocity motion, you really only have one equation for constant velocity motion in any particular dimension. If you have constant acceleration, that motion gives you three equations. And so making sure that we get the right equation depending on the type of motion we have in the problem will be sort of one of the first critical steps in terms of making sure that we're working problems correctly.